This is the second video on section 4.10, velocity and acceleration vectors. So we're going to look at example 116. We've launched an object from the ground at a speed of 100 feet per second at an angle of pi over 4 with the horizontal, and the only force acting on the object is gravity. So part A is to find the initial velocity vector. We're given this pi over 4 in the problem, and we're given this 100. Just using right triangle trigonometry, we get 50 square root of 2 and 50 square root of 2. So our initial velocity vector, this is a velocity at time 0, is this vector here, 50 square root of 2, 50 square root of 2. For part B, we're asked to find the acceleration vector. So we start with the initial acceleration. Remember, the only force acting on this is gravity, so this is our acceleration vector. So we find an antiderivative of this vector and add the initial velocity vector. And that gives us our velocity at time t. This is very similar to the things we did in Calculus 1, except we're working with vectors instead of just simply position functions. Part C, we want to find the function that gives us the position. So we find an antiderivative of velocity and add the initial position. But the initial position is 0, 0. So we take an antiderivative of velocity here, and then typically we would add an initial position here, but our initial position is 0, 0, so I didn't do that because I want to save board space. So typically when you find this, again, you have to compensate for your initial position, but our initial position is the 0 vector. So I did not add the 0 vector here. For part C, we want to find the maximum height of the object. There are a couple of different ways to do this. I took the Calc 1 approach. You take your height function, calculate the derivative, set it equal to 0 to look for critical numbers. Our one critical number is a solution to this linear function, which is 25 square root of 2 divided by 16. Substitute that into the height function. That's our maximum height. That's one approach. The second approach, which I didn't put on the board, is this. Your height function is a quadratic. Has a negative first coefficient. It's a quadratic that opens downward, so find the vertex. The maximum value of this quadratic occurs at the vertex. That's another approach to this. Either way, our maximum height is 78 1/8 feet. D is to find the horizontal range. So in order to find out how far it goes, we want to see what the time is that it impacts the ground. So we want the time of impact. So how do we find that? We take our vertical component and set it equal to 0. That's when the object's on the ground. This has two solutions, one of which is 0, but we don't care about that one. That's where it starts. The other one that we do care about is 25 square root of 2 divided by 8. This is the time that the object hits the ground. If that's the time the object hits the ground, now the question is, where does the object hit the ground? Well, the object hits the ground at s of 25 square root of 2 over 8. Now we were only asked for the horizontal range, so we're just going to look at the horizontal component here. The vertical one is of course 0 because it hits the ground there. So we were asked for the horizontal range. The last thing we're asked is for the speed of impact. This is our velocity. Magnitude of velocity is speed, and so to get the speed of impact, we want to substitute the time that it hits the ground into this function. And we've calculated the time that it hits the ground in the previous part. So we substitute that into the velocity function and and calculate the magnitude. And that simplifies to 100 feet per second.